earlier, we found that the angular momentum is equal to the rotational inertia times the angular velocity, which is just like the linear momentum. It's analogous to linear momentum equaling mass times linear velocity. So angular momentum equals rotational inertia times angular velocity. And we also found that the rotational inertia is now the mu times the r squared. And we also found that kinetic energy is equal to angular momentum squared over twice the rotational inertia. So very, very, very important relationships for rotating systems. The angular momentum is given by rotational inertia times angular velocity. The rotational inertia is actually given by the reduced mass times the r squared, the distance between the two masses. And again, we're treating this as if it's a single mass of reduced mass rotating about a fixed center. And the kinetic energy of this rotational system is equal to the square of the angular momentum divided by twice the rotational inertia. And again, the rotational inertia is given by this mu r squared. Now, there is no potential term here. There is no potential energy term, notice. Potential energy term. For some diatomic molecule that's just rotating in free space in any orientation, it actually doesn't matter, there is no potential energy term for this. So there is no potential energy term because there are no external forces. Because there are no external forces on the masses. Now, if we want to, we can certainly put these molecules in a magnetic field and create some external forces, but as it is just a rotating molecule, there are no external forces. So, the orientation of the rigid rotator, and when we say rigid rotator, we're just talking about the thing that's actually turning, you know, the diatomic molecule, whatever it is we happen to be discussing. The rigid rotator, which is just the molecule. So the orientation of the rigid rotator does not affect the energy. Does not affect the energy. Because there is no external force, so it doesn't matter how it's rotating. It doesn't change the energy of the rotating system. Now, since there is no potential energy term, the Hamiltonian, excuse me, the Hamiltonian of the rigid rotator is just the kinetic energy operator. Is just, not the K, let's just call it, is just K, the kinetic energy operator. The kinetic energy operator. So we have the Hamiltonian is, you know what, I make the worst Ks. The kinetic energy operator, which is going to equal, remember, minus h bar over 2m, but now it's twice the reduced mass, and then, of course, delta squared. That's it. So again, this is just the initial discussion. Next lesson, we'll continue on and talk about the Schrödinger equation. Thank you so much for joining us here at Educator.